Hello friends, good afternoon and welcome to DSET live lectures. Dear friends, today in coordination chemistry, we will be talking about crystal field stabilization energy of complexes with strong field and weak field ligands. To discuss this topic, we have with us our subject expert, Dr. Ajay Bhagi. Dr. Bhagi is Associate Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome, sir.
Thank you. And in this series of coordination chemistry, today we'll be covering a very important topic of coordination chemistry. This is crystal field stabilization energy of complexes with strong field and weak field ligands. And we'll be dealing with two geometries today, octahedral and tetrahedral geometries. And before we really come to the real topic, there is a need, because to understand this particular topic, there is a need that we revise a little bit of what we have learned in the crystal field theory by now. So what we have learned is that under the influence of a crystal field, whether it is octahedral or tetrahedral, the metal d orbitals interact differently with ligands field, resulting into splitting of degenerate energy levels of d or f orbitals into new sets of orbitals or states. And if we go by the different geometries, then under the influence of octahedral field, 5 degenerate d orbitals are split into two sets of energy levels, that is T2G and EG. And under the influence of tetrahedral field, these 5 degenerate energy levels, they are actually being split into two new energy states, that is E and T2. And the gap between the two energy levels, that is the extent of separation between the two energy levels after the degeneracy has been lifted, is denoted in terms of the 10 dq or del values. Now, knowing this, when the electron starts filling into these various orbitals for the systems from D1 to D10, what do we expect therefore is that energy would vary for every individual system. And that is why it is very important that when we know how much is the energy variation from a system to system that has taken place, will explain or help in understanding the stabilization of a complex that has taken place. Now, just to have a sort of a revision once again for the splitting, with a condition that how much is the change that energy is taking place from the barycenter. Now we know there are 5d orbitals. They are already in a higher energy state from the free ion under the influence of a crystal field. And when we examine that is the average energy increase is same for all the 5d orbitals, then we have already learned that no, you have two different sets of orbitals. One is called T2G set of orbital, which from the barycenter is stabilized by 0.4 of del octahedral and in the octahedral field, and of course 0.6 is the destabilization. So there we have to concentrate. Now, knowing these variations, if the electron starts filling into the lower energy level of T2G first, followed by the EG, then of course for every number of difference in electrons, we are bound to get variation in energies as well. Just for your benefit, I am also once again, just showing what is the splitting diagram that we have learned for the tetrahedral complexes. Now, once again, there are 5d orbitals. They are being split into E and T2 state energy states. In E, you will appreciate that they are stabilized by 0.6 del T, and that is why, because it is being stabilized in terms of energy, so minus sign has been put before 0.6. We also understand that if this del T is being taken as 10 dq, then this will be called 6 dq stabilization, and this will be called 4 dq destabilization with reference to the average energy of the d orbitals. And we have also seen that how the del T and del O, they are normally related to each other. Approximately, it is the half separation if the ligand and the complex is same. It is the half separation in case of a tetrahedral complexes in comparison to the octahedral complexes. Nearly it is 4 by 9 of del O. We also have to understand and revise that factors which can affect the separation between the two levels is also important when the final energy of CFSE is being calculated. Now here the charge on the metal ion is therefore important. Higher is the charge, greater is the attraction between the ligand and the metal electron density, and therefore the magnitude of 10 dq increases. Now when you come to the number of ligands, that is whether it is a tetrahedral complex or an octahedral complex, there once again you will appreciate that more is the number of ligands, greater will be the separation between the T2G and the EG level. And third, of course, is very important factor, that is called nature of ligand. Now all ligands, they are not going to have a same kind of influence on the d orbitals of the metal. The variation is going to be there with how strongly that ligand can behave so as to bind with a particular metal ion. Now when you are examining this, we have already talked about the factors which can affect 10 dq. You may have seen the spectrochemical series, and we know that the ligands like cyanide, carbon monoxide, phosphines, they are strong field ligands. They are being labeled as strong field ligands through the spectrochemical series, whereas there are certain ligands which are of moderate field strengths, like they are normally oxygen donors, and the halides, the haloatoms, when they are bound to the complexes, they act as a weak field ligand. Now of course the ligands do change little bit of their nature depending upon the metal as well. The fourth factor which is very important for this is the period to which the metal ion belongs. Now this, what I mean to say here is whether the metal ion which is being forming a complex belongs to the 3D series of the transition metal, 4D series or the 5D series. Now if it is 3D, 4D or 5D, bigger the size of the d orbital means they are going to be influenced more under the field, that means under the crystal field, and hence the 10 dq value for 4D or the 5D respectively is going to be greater than that of the 3D. We also understand if you compare the sizes, 4D, 5D, they are normally of a almost similar size because of the lengthenite contraction. Now let us once define what do you mean by crystal field stabilization energy. We have seen that there is an average energy which is being labeled as a barycenter. Now after the distribution of electron into the various energy levels that we have already seen that resulted because of the upliftment of the equal energy levels. So what do we do is therefore we define crystal field stabilization energy in terms of the crystal field stabilization energy is measure of net energy of stabilization that is gained by a metal ion, non-bonding d electrons as a result of complex formation. So complexation, how stable it will be, has something to do therefore with the crystal field stabilization energy as well. It is also being defined as the energy of electron configuration in the ligand field minus the energy of electronic configuration in the isotopic spherical field. So this we need to therefore consider when you are defining the crystal field stabilization energy. Now there are certain factors which can influence the CFSE. As we have seen, the 10 dq value are being influenced by certain factors. The CFSE therefore is also going to be dependent upon some of the factors. And the first is the geometry. Now whether it is tetrahedral or octahedral, that is going to decide based upon the number of ligands that how the electrons are being distributed between the T2 and the E levels and T2G or the EG level in octahedral case. Similarly, it is also going to depend upon the number of d electrons. So number of d electrons you cannot ignore. I mean, if you have a system where there is only 1, 2 or 3 electrons in an octahedral field, all three are likely to occupy the T2G set of orbital, therefore there will be a greater stabilization. But as the fourth electron comes, if it occupies the E level, of course it is the destabilization. So number of d electrons and which particular T2 or the E set they are actually occupying is going to decide the overall crystal field stabilization energy. Similarly, you also talk about ligand field strength. I mean, here the nature of ligand, as I told you, is very important. Whether it is a strong field ligand or a weak field ligand, that can also give rise to the variation in crystal field stabilization energy, as we'll see with case to case. And the last but not the least is very important here is the pairing energy. Now, pairing energy is energy which is being consumed for making two electrons getting paired in a same orbital. Now, whenever such a pairing of electrons takes place, because both are negatively charged, that doesn't come free. It comes at an expense of some energy, and that is being labeled as pairing energy. Okay. Now, let us see how the electrons are distributed in d orbitals in an octahedral field. Now, these diagrams, in short, exhibits how the electrons would be distributed. When there is a strong field ligand that is present, the separation between the T2G set of orbital and the EG set of orbital would be larger in comparison to when there is a weak field ligand present, like chloride, bromide or iodide. Here the strong field ligand can be cyanide, carbonyl, phosphine, etc. So when the separation between the T2G and the EG is larger in comparison to this, when we talk about the one electron system, that is like titanium 3 ion. Now, titanium 3 ion has only one electron in the D. Therefore, it has no choice but to occupy the T2G set of orbital. And hence, the configuration wise, if you look at the first case, what do we get is T2G1 configuration, whether it is a strong field ligand or a weak field ligand. When we measure this kind of energy, CFSE, it may appear to be same as minus 4 dq in terms of CFSE, but since the dq value is going to depend upon how is the separation, how much is the gap between the T2G and the EG level, therefore 10 dq would vary in both cases, hence dq value would vary, hence the average energy CFSE is going to be changed whether it is strong ligand or a weak field ligand. Similarly, if you look at D2 configuration, now in D2 configuration, we have T2G2 type of a configuration that appears. Now, T2G2 type of a configuration means that there will be two electrons in the T2G orbital, and whether it is strong or a weak field, the Hund's rule has to be followed, the spins have to be the parallel, they have to occupy different orbitals in the same sub-level of the energy, and that is why we get T2G configuration with the two parallel spins as shown for the D2 configuration here, whether it is strong field or a weak field case. Similarly, for D3, so from D1 to D2 to D3 configuration, what do we are seeing from the diagram is whether it is a strong field ligand or a weak field ligand, ultimately all three electrons, 1, 2, 3 electrons, they are going to occupy the T2G set of orbitals and the EG remains vacant, and we have therefore variation in CFSE arising because of both the factors, that how much is the gap, how much is the 10 dq value, that is going to decide the CFSE, and secondly, how many number of unpaired electrons or the electrons are present in a system, that is going to decide. The situation gets a little complicated, specifically in octahedral complexes, as we go further. Now you are talking about a D4 configuration. In a D4 configuration, what actually is happening is that T2G and EG, they are being separated from each other by some margin for a strong ligand and for a weak ligand. Now both the possibility in such a system exist. It may happen that the configuration becomes T2G4. That means all 4 electrons, once one single electron in the 3 of the d orbitals of the T2G set, they have been occupied, then the pairing itself in the T2G set starts. Now when it happens, we call such complexes to be low spin complexes, because in T2G set of orbitals the pairing has started. But it may happen if the 10 dq value between the T2G and EG is lesser, then instead of getting paired up, the electron may go to the E state also. So, both the type of configurations, although for D1, for D2, for D3, the configurations were same, whereas in D4, in strong field case, the configuration becomes T2G4, whereas in weak field case, that configuration becomes T2G3 and EG1. Now, just to elaborate this particular example, let us go a little further in this, how and what is happening in D4. And when one particular configuration will be more preferred over the other. Now, here the pairing energy of this electrons, that becomes very important. If it is a strong field case, usually a low spin complex with two unpaired electrons that is being formed. You can see from here that when T2G is orbitals, one of the T2G set of orbital is doubly occupied, rest of the two they are singly occupied. So, one can say that in such a case there is a low spin complex that is being formed, because if you look at the magnetic moment of this complex, the magnetic moment would be equivalent to that of the complex or a ion which is comparative to two unpaired electrons. Similarly, if you look at the second part of the diagram, you will appreciate that there are four unpaired electrons now in a weak field case. So, there are four unpaired electrons. So, magnetic moment of this complex when there is a weak field is going to be much higher than the first case. So, comparison is quite clear. But which configuration is preferred? When that depends upon whether the pairing energy is less than that of the gap between the T2G and the EG, that is being called del O for octahedral complexes. So, when the pairing energy is less than del O or 10 dq value, in such a case we therefore conclude that a low spin complex would be preferred, and when the pairing energy is larger than del O, in such a case there is a weak field case that is possible and four unpaired electrons are there, a high spin complex ultimately would be formed. So, pairing becomes difficult because pairing energy consumes more energy than placing an electron into the higher EG level. Hence, what do we conclude is that 10 dq value, whether it is more than P or 10 dq value, whether it is less than P, is going to decide whether a strong field case low spin complex is formed or in a weak field case a high spin complex is formed. Now, let us start calculating the CFSEs for various octahedral complexes with from D1 to D10 configurations. We now know how the electrons are likely to be distributed among the various levels. So, it will be very easy for us to understand the magnetic properties of a complex, as well as it will be very easy for us to calculate the CFSE in terms of dq or del O values. Now, look at this figure and the table. Now, here when you have one electron, as we know in an octahedral complex, there will be one electron as we have understood. The spin state is going to be the half, and therefore, the complex is expected to be paramagnetic. And in this paramagnetic complex, the magnetic moment would be in the somewhere in the range of 1.73. CFSE, if you see from the barycenter, since it is minus 0.4 del O or minus 4 dq lower than the barycenter. So, simply I say CFSE is minus 4 dq or minus 0.4 del O. Similarly, for D2 ion like that of anything like titanium 3 plus can be the example of let us say D1. So, titanium 2 plus can be an example of this. Now, there are two electrons in the D, and therefore, when we calculate the CFSE, you can see the CFSE comes out to be minus 0.8 del O or 8 dq, and since the S value becomes 1, magnetic moment would be somewhere in the range of 2.8 Bohr magneton. So, we know the two things from this distribution of electrons into the T2G and the EG levels. Not only we can calculate the CFSE, but we can also comment upon the magnetic moments also. Now, coming to the D3 configuration, once again the third electron also enters into the T2G as we have seen earlier. So, while calculating, you can see the CFSE therefore is minus 1.2 del O or minus 12 dq. Again I repeat, kindly remember this dq value can change with the change in the charge on the metal, or it can also change with the change in the ligand, and all those factors which can change 10 dq value for a particular complex. Now, as we have seen for the D4, there were two possibilities. The arrangement now we know as discussed earlier, but when we calculate CFSE, there will be a difference. The difference is for a low spin complex, since each one of these is lower by 0.4, so 4 multiplied by 0.4 becomes minus 1.6 del O, but also a pairing. This may be stabilization, but at the same time, this pairing has caused some energy consumed in the process of pairing, therefore plus P. So, one electron gets paired, so one of the P that is being added, whereas in the high spin case, the CFSE, 1, 2 and 3 electrons, they are being stabilized up to minus 1.2 del O, but at the same time, the fourth electron in the EG state is going to have a destabilization of 0.6 del O. So, overall, it will be minus 0.6 del O. So, the simple calculations can tell us the energy stabilization from these 3 electrons and the destabilization from this 1 electron for the D4 would ultimately tell us how much will be the CFSE for the high spin state. Now, as I told you, one is going to preferred over the other. It depends upon the pairing energy. Normally, it has been seen the pairing of electron in the d orbital in terms of centimeter inverse per electron is 14,900 centimeter inverse. So, if the pairing is that of the del O, both are equally stabilized, and other factors therefore can control whether the complex would be high spin or low spin. If the pairing energy is more than del O, in such a case, high spin weak field complex will be stabilized, and if it is low spin weak field, that means the P is less than del O, then in such a case, we will see that this kind of a situation, low spin kind of a situation that results. Okay. Now, going a little further, you can now very well imagine if we have a situation and if we know how the electrons are being distributed into T2G and EG sets of orbital from the type of calculations that we have done for D1, D2, D3 and D4, we can also calculate CFSE for all these complexes, like with a D5 ion, iron 3 may be a example of this, D6, iron 2 may be the example of iron 2 ion, maybe at the center of a complex, that can be an example of the D6. The cobalt 3 can be an example of D6. Similarly, cobalt 2 ion can be an example of D7, nickel 2 can be an example of D8 and so on and so forth. Copper 2 can be example of the D9 system, and zinc 2 ion can be an example of D10 system. Now, once you are able to designate the distribution of electrons into the T2G and EG correctly, thereafter, knowing the gap between the energy from the barycenter, it will straight away help you in calculating the CFSE for each case, and also looking at the distribution of electrons and knowing how many number of unpaired electrons are there in low spin or a high spin state, one can straight away comment on the magnetic properties of a complex. Now, coming to this D5 case, if you closely look at the low spin complex for iron, in such a case, what you are finding is all the 5 electrons, they are present in the T2G set of orbitals, and hence we have to see that it is minus 20 dq plus 2p. That is a sort of an energy CFSE that we are going to get. Whereas in D5 case, you can see from here these T2G, there will be minus 12 dq is the stabilization, and 2 electrons in the EG and plus 12 dq is the destabilization. So, in D5 case, the CFSE therefore becomes 0. Now, this is a case where you have 1 electron half-filled configuration in lower and above, that means T2G and EG energy states, and hence the net energy stabilization achieved is found to be 0. This is what it helps in understanding many properties of the complexes if we can measure the magnetic movement as well as the crystal field stabilization energy for complexes. It helps us to understand the magnetic properties and the spectral properties of complexes, and one can, knowing the value of 10 dq, one can in actual terms calculate the energy. If the energy values for 10 dq, they are being known to us in terms of, let us say, centimeter inverse, one can multiply that quantity with 83.6 value so as to convert it into a kilojoules per mole sort of equation. Now, similarly, you just look at D6 case. In D6 case, now this is a very peculiar situation where with a high spin complex like here, there are 4 unpaired electrons. That means D6 high spin, that means with a low field intensity, low ligand field, we may have a complex to be highly paramagnetic. Highly paramagnetic means it has 4 unpaired electrons. But look at when you have a low spin state, there is all the 6 electrons, they are being paired into the T2G orbitals, and hence this is going to be nearly diamagnetic complex. And for cobalt 3 ion, we have seen with a ligand like cyanide, with a ligand like even ethylene diamine or even ammonia, in this case, the complexes are found to be diamagnetic, whereas complex like COF6 3-, that means with a ligand like fluoride or iodide or weaker ligands or even aqua complexes, what we have found is complexes to be highly paramagnetic. This is a differentiation. Now, similarly, if you want to calculate the CFSE for this, we can have the simple formula also that will show you, but you can say minus 24 dq because 6 electrons are in the T2G sets up. So, minus 24 dq plus 3 pairing energies, so plus 3p, that ultimately tells us how much is the CFSE in this case. One can keep on calculating for CFSE for D7, D8, D9 and D10. For D10, as you have seen, there is a symmetrical distribution of electrons in both the energy states. Therefore, the CFSE comes out to be 0. In D8, D9, D10, kindly remember that there is only one type of distribution, whether it is the weak ligand or a strong ligand, number of unpaired electrons remains the same. Here it is 2, in D9 it is 1, in D10 it is 0. So, therefore, what from this distribution of electrons in the various levels we conclude, it is the D4, D5, D6 and D7 ions. These type of systems are going to exhibit low spin or high spin situations, and not D1, D2, D3, D8, D9, D10. They are going to exhibit only one type of energy state, and that is the high spin energy state. Now, going a little further, if by now we have understood the distribution for octahedral complexes, so what we can say therefore is that generally the T2GX and the EGY configuration, as we can label it for the various D1 to D10 systems, this will give us the overall net energy for various configurations of CFSE, and here is the formula in the next slide where you can calculate this formula so as to know how much would be the CFSE for various number of electrons into the T2G. X is the number of electrons into the T2G, so it has to be multiplied by minus 0.4, and Y is the number of electrons into the EG set of orbitals. Now, whatever is the del O value, we therefore can tell us how much is the CFSE that is coming, and if at all there is any kind of a pairing that has taken place, it has to be subtracted out of this. So, NP becomes number of paired electrons, how many pairings have taken place, that can be added. Now, here del O of course is 10 dq. Similarly, number of electrons in T2G multiplied by 0.4 del O. In the simple terms, I can write this plus number of electrons in EG for 0.6 del O NP. This becomes therefore a general formula in general to show how much will be the CFSE in this case. So, we take a break here and then we will continue. Welcome back. Now we'll continue from where we had left in the last session, and here is the example. Now we are presuming a D6 case, low spin situation. In low spin situation, you can very well appreciate that CFSE, if it has to be calculated, it is to be 6 multiplied by minus 0.4 del O. So this becomes minus 2.4 of this, and 3p is added here because there are 3 pairings that have taken place. Similarly, in a high spin state, there is only one pairing, so 1p, but just look at, there are 4 number of electrons into the T2G, so 4 multiplied by 0.4 del O plus 2 multiplied by 0.6 del O, that is going to decide in a high spin state what is the overall CFSE, which comes out to be 0.4 del O plus P. Okay. Now just look at the factor that became very important during our discussion, that CFSE is going to depend upon the pairing, number of pairing that is taking place, whether the complex formed will be the low spin complex or whether the complex that has formed is a high spin complex is ultimately going to decide the overall. Therefore, we also need to understand what are those factors on which spin pairing energy depends upon. Now, there are in fact 2 factors which are broadly responsible for the spin pairing, whether it is going to take place or the pairing energy, that is, it is going to play a role. Now, as I told you that it has some average value somewhere around 15,000 centimeter inverse for the d orbitals, but in short, what do we say is that the spin pairing energy usually depend upon the Coulombic repulsions. Of course, as I told you, both the electrons, they are negatively charged. When they are going to be placed in the same region in space, that is the orbital, they are likely to repel each other. When this repulsion will be overcome by forcing electrons to occupy the same, so we say that in which type of orbital it is present. We expect therefore with a orbitals with a larger size, like if the electron is present in a 5d orbital, it is going to have a lesser repulsion when it is going to occupy a little smaller size d orbital like 3d. So we therefore have to take into consideration the Coulombic repulsions faced by the 2 electrons which are occupying the same orbital. Here you can very well see that therefore 3d orbital pairing energy would be larger than 4d and 5d. Similarly, it is going to be larger than that of the f orbitals. Second is, of course, very important in pairing energy is the loss of exchange. If you have more number of unpaired electrons for any system, the number of exchanges with the same spins would be greater in number, and therefore the exchange phenomena is going to give us more of exchange energy. We all know that Hund's rule has its own importance in the understanding of various configurations that we get for a system, and it is not the simple atom or ions. Even in complexes, when these d orbitals are going to be occupying or having a various type of electronic configuration, the loss of exchange energy is going to be important. In low spin state, of course, the pairing is going to take place. Number of unpaired electrons or the identical atoms are going to be lesser. In such a case, there will be a loss of exchange energy, and hence what do we say is the exchange energy of Hund's rule says it is proportional to number of electrons having the parallel spins. The greater the number, the more is difficult it becomes to pair the electrons. Therefore, if you look at a D5 system with a manganese 3 and manganese 2 configuration, what we are going to get is we are going more likely to form a high spin complexes with a weak or a model field ligands. Of course, there can be a possibility of a pairing if the ligand strength is very, very high, and we do encounter a cyanide or a carbon monoxide or a phosphine type of ligands, even resulting pairing in such case, such electronic configurations also. Now, these are the, in the table you can see from here, the next table that you will see, the pairing energy of gaseous 3D metal ions for specifically the configurations where we have a low spin and high spin situation. They are, of course, situations, they are electronic configuration of D4, D5, D6 and D7. Just see manganese 2 ion, the metal 2 ion, where you can have a chromium 2, manganese 2, iron 2 and cobalt 2. The pairing energy values, the average pairing energies are given here. If you have the M3 ion, in such cases also you can have D4, D5, D6 and D7 systems. That means the number of electrons available in the D. You can see that the pairing energy has increased. Now, going from lower oxidations to the higher oxidation state, that has caused more attraction between the nucleus and the electrons. Therefore, the d orbital size, as it starts contracting, the electrons which are going to be pair up between these two contracted d orbitals because of an increased effective nuclear charge. Therefore, what we are going to expect is the pairing energy is going to be enhanced. It is seen for a D4 system, the chromium M2 ion and M3 manganese 3 ion, the pairing energy has increased from 23,500 centimeter inverse to 28,000. This kind of a trend is very common. You can also see some kind of a variation even in this D4, D5 and D6, D7 system, but this appears to be more random. Now, the pairing energy in complex are likely to therefore 15 to 13% lower due to the covalency. Now, when these ions enter into the complexation, the value starts reducing and the average value is 22%. These values are average 22%, it's too high. You can also now summarize whatever we have learned about the octahedral complexes in this particular table. You see that CFSE for octahedral complexes, whether for D0 to D10 configuration, of course, when there is no electron, we are not going to get any CFSE. That means the crystal field stabilization, there is no question whether it is weak field or strong field. The examples are calcium and scandium ion. You can very well see CFSE. Since there is no electron in the T2G in the EG, there is D0 configuration, hence there is no question of CFSE. Look at D1, the CFSE or the LFSE, ligand field stabilization energy, comes out to be minus 4 dQ, and even whether it is strong or a weak. But remember, once again I am repeating this, that depending upon the 10 dQ value, the separation between the T2G and the EG, the dQ can vary. If the dQ can vary, so will be the minus 4 dQ value, and if the 4 dQ value, my dQ with the change in dQ, that is going to vary. So we do not expect in terms of kilojoules per mole the identical energy for a weak or a strong field ligand, and there can be therefore a very large range of energy variations even for a D1 system, that with a change in ligand or with a change in oxidation state that can be encountered. Now, similarly for D2, T2G2 minus 8 dQ, vanadium 3 is the example. For D3, chromium 3 is a main example. For D4 system, chromium 2 is a main example. And look at how the CFSE with the increase in number of electrons in the T2G, even for the weak ligands, that kept increasing till D3 minus 12 dQ. But as the electron starts entering into the EG state, it starts increasing and reached once again at a D5 case at a 0. Once again, it has gone from minus 4 to minus 8 to 12 and then with to minus 6 to 0. So you can see from this variation here that what actually is happening is that CFSE is constantly increasing. Similarly, for strong ligands, when there is a spin pairing, that means electrons are getting paired up, we can see that it keeps increasing till D6 state. That means the number of electrons are actually occupying T2G set of orbital. The various examples for these states are there. Now, with the strong ligands, these are type of the LFSCs or the CFSEs that we are going to encounter. But thereafter, once we have reached to D6 state, the 7th electron has no option but to enter into the EG state, and destabilization starts and the value starts decreasing, and ultimately to D10 configuration it reaches to 0. Now, here the variation in LFSE, that becomes very important if you want to understand the variation in their spectroscopic properties and the magnetic properties, because it all depends upon the distribution of electrons into the T2G and the EG state. Now, let us then try to apply this concept to the real complex situation. First example that we have taken is that what is the CFSE for a complex which is a cyno-complex of iron. Now, in case of this complex, you can see since there are 6 cyno-ligands, so coordination number here is 6 and the complex is octahedra. In octahedra situation, we very well know that what would be the splitting pattern. That means it is going to be T2G and EG splitting pattern. Now, knowing how many electrons would be there in iron 3, now iron 3 of course is going to have 5 number of electrons in the D. When it has a 5 number of electrons in the D, and therefore it becomes in a low spin state, in a high spin state, it is going to have a T2G3 and EG configuration. Whereas in a cyanide being a strong ligand, it is going to cause a pairing, because separation between 10 DQ between T2G and EG is going to be large. When that separation between the T2G and EG is large, that means 10 DQ is larger, we expect a low spin complex being formed. Now, had iron been in this particular format, the CFSE would have come out to be 0. But since cyanide in this case is a strong ligand, 10 DQ is larger, so what do we get is the CFSE is 5 into 0.4 del O plus 2 pairing that has taken place. So, it is 2.0 del O or 20 DQ plus 2P. So, that becomes the equation. Look at the second example. Here, it is a cobalt 2 ion which is being surrounded by 6 aqua ligands. Now, here once again, if we know the CFSE, can we comment upon what spin state it has? Yes, because both the spin state you can write and then calculate the CFSE and match the observed CFSE with the spin state complex. From here, once again the coordination number in this complex, because there are 6 aqua ligands, so coordination number is 6, the complex is octahedra, and there are 7 electrons in the D. When there are 7 electrons in the D, so if there is no pairing taking place, aqua being a weak ligand, so there is no pairing taking place, high spin complex is likely to be formed, but we want to know whether it is true or not. Now, in this case, as you have found, you can see from the calculations 5 electrons in the T2G set and 2 electrons in the EG, 2 pairing have taken place. So, it is minus 0.8 octahedral 2p. So, this is what is going to match with here, whereas in this case you can see had it been in a low spin state, the CFSE would have come out to be minus 1.8 del octahedral plus 3 of the p. So, you can very well see from this whole situation that we can comment upon whether it is a low spin complex or a high spin complex, knowing the CFSEs, and knowing CFSE therefore has helped us to understand complex situation and the distribution of electrons also. Now, in this whole of this thing, when we are calculating the CFSEs, we had been constantly talking about the magnetic behavior also. So, it is good for us if we also understand that magnetic moment, a word that we have constantly repeated, what actually it depends upon and how it is being calculated depending upon the number of unpaired electrons in the various system. The magnetic moment normally being designated as mu for a complex with a total spin quantum number s, and we understand the magnetic moment mu is given by this formula, that it is 2 is a gyromagnetic ratio here, s into s plus 1, it's under root, and mu b is in the Bohr magneton, that is a unit, and we know that the mu b in terms of Joule Tesla, it depends, its value is 9.274 10 to the power minus 24 Joule Tesla inverse. So this is in SI system if we want to calculate, and normally if we designate the magnetic moment in terms of Bohr magnetons, then depending upon the value of S, which is of course is going to depend upon the number of unpaired electrons in the present. Here is the how to calculate the S. If let us say the number of unpaired electrons are 5, then it will be half of the 5, so 5 by 2. Now you know the value of S, you substitute the value of S in the formula so as to calculate, and when we do so, we understand that 1.73 is the value that we get for the 1 unpaired electron, and for 5 it is somewhere around 5.94. We will see from the table. Now this value, therefore, straight away instead of putting the value of S, one can use this formula knowing the number of unpaired electrons so as to calculate the Bohr magneton value for the magnetic moment value in terms of Bohr magneton for various systems. In D4, D5, D6 and D7 octahedral complexes, magnetic moment can verify easily whether to predict a weak versus strong ligand. That means if you can find out the magnetic behavior of a complex, you will be knowing the spin state. So from direct knowing the spin state, we can also therefore predict the crystal field stabilization energy. So there is a relationship that existed between what spin state it has and to the ultimately what magnetic moment that we can find from the experimental means by measuring the magnetic susceptibility. Once you measure the magnetic susceptibility experimentally, you can convert that magnetic susceptibility value into the magnetic moment value, and knowing the magnetic moment value, once you know what spin state it has, it will help us to understand that what is the distribution of electrons into the T2G and the EG set of orbital. Ultimately, that will help us to calculate the CFSE, that is the theoretical. There is also a possibility so as to calculate CFSE experimentally. What for that purpose you have to do is, you know how is the distribution and what is the 10 dq value. That 10 dq value we have seen in the previous sessions that it can be calculated from the spectroscopic techniques. Absorption spectra for the complex can help us to calculate 10 dq value. Once you know the 10 dq value, you can calculate dq and substitute that dq value in a theoretical calculations that we have seen for various octahedral complexes, and from there, therefore, we'll be able to calculate the CFSE. Now, we have to know that the tetrahedral complexes, only and only high spin complexes are formed. Why? Because del T is very, very smaller than del O, and in no circumstances, therefore, del T becomes larger than the pairing energy. So it is always smaller than the pairing energy, and hence only high spin complexes would be encountered. Please look at, these are the calculated values for various ions forming the complexes, and number of unpaired electrons are listed here, 1, 2, 3, 4, 5. Value of S is also being listed. I can substitute either in this number of unpaired electrons in this formula or the earlier formula that was based upon the S value. From the S value you can substitute there so as to calculate the magnetic moment theoretical values. Theoretical values comes out to be 1.73 for 1 unpaired electron, 2.83 for 2 unpaired electron, 3.87 for 3, 4.90 and 5.92. Now interestingly, the D6 configuration would have 4 number of unpaired electron, D7 would have 3 number of unpaired electron. Likewise, there can be D8, D9 situation, or a D10 there will be no unpaired electron, so it is likely to be diamagnetic. Now similarly, for low spin complexes also, based upon this, knowing number of unpaired electrons for various complexes, the calculations can be made. You can see from here, there are certain variations, experimental values we are observing here. They are for various reasons. There is some kind of a quenching that can take place. There can be some orbital contribution that can increase the calculated value, because what we are listed here is the spin-only value for the magnetic moments. We have not taken into consideration the orbital contribution that can come to the magnetic moment values which are experimentally determined. There can be a quenching because of a restricted movement of electrons in a complex situation. So values need not, therefore experimental values need not exactly match the theoretical values. They are always being found for various complexes into certain ranges. Normally these are the ranges. Even if it comes out to be lower than, a little more lower than this, that means there is one unpaired electrons. In such a situation, it may have happened that a movement of electrons was restricted and no clear orbital contribution was therefore coming. Now, these are therefore the values which are normally encountered, not very specific. You can see from here for iron 3 like of a complex, there is quite a bit of restriction, and the value, the spin-only values have even not been achieved in case of iron 3 complexes. So they therefore help us to understand the distribution of electrons into various octahedral complexes. Now, based upon this, therefore, we take two examples which will help us to understand what actually we are trying to communicate. Now, here we have an iron complex, iron 2 complex, which is a aqua complex, and in iron 2 complex, of course, what we have found is that the Bohr magneton value, that magnetic moment values are very, very high, that is 5.26. The number of unpaired electrons are 4. So this helps us to understand that these coordination compounds, they are high spin complexes. Whereas with a strong ligand like cyano, when all 6 electrons of the iron 2, they have got paired up, so it is almost near to the diamagnetic situation. And in diamagnetic situation, we know number of unpaired electrons are 0, so the magnetic moment values are going to be nearly 0. If we do not get even 0, it is going to be near to 0. But theoretical calculated value, of course, is 0 Bohr magneton. Now, this particular table also helps us to understand the low spin and high spin situation. This is a cyano complex and aqua complex that we have talked about. Now, one more very interesting graph or a comparison that can be found from this particular diagram. You try to see these alpha, these are not actually the orbitals, d orbitals that we were not normally being drawing. These are the energy states. Alpha means a particular spin state and beta means the reverse of the first spin state. If it is clockwise, beta is going to be the anti-clockwise spin state. Now, I have written these two spin states that may be separated by the pairing energy, because whenever the pairing would take place, in every system there is going to be a clockwise spinning electron and an anti-clockwise spinning electron. So these spin states therefore are going to be separated by the pairing energy. Now, in case these spin states are situated and under the influence of this crystal field, they are being broken into T2G and EG. These spin states, 5 spin states, have been broken down into T2G and EG, and if there is overlap of this in such a case, that means when this pairing energy is smaller, then there is going to be an overlap. So all 6 electrons would be either occupying alpha, alpha, alpha and the beta, beta, T2G energy states. So pairing would be resulted. When the T2G is fully filled, then the electron starts entering into the EG with a alpha spin state and then anti-clockwise beta spin state. So pairing would then take place in the EG. This diagram actually helps us to understand the relationship between the pairing energy and that of the spin states which are possible for a octahedral complex. Now, when the P is larger, this overlap is not going to take place. So in such a situation, what is going to happen is that 3 electrons would enter into T2G spin state, and then 2 into the EG with the alpha and all alpha. That means all the 5 electrons would have a clockwise spin, and 3 electrons would occupy T2G state and 2 electrons would occupy EG state. And thereafter, once these 5 electrons have entered into T2G and EG set of orbital, then the pairing once again would start from the lower energy state, that is the T2G. So 6th electron is going to occupy the T2G energy state, 6th, 7th, 8th, 9th and 10th. So accordingly, as the number of electrons keeps on increasing, the pairing would take place, but not before each of the T2G and the EG gets 1 electron each. So this actually helps, this diagram helps us to understand that what would be the situation or a comparison between the strong field and the weak field cases, and each line here is actually denoting the not the orbital, but it is the 1 electron wave function that with a spin alpha or a beta. Similarly, now just from that very diagram, if you try to have a justification for a system like which have 6 electrons in the D, and if it is a strong field case, in a strong field case, the P is going to be smaller, the T2G and the EG spin states are going to overlap or crossover from each other. So all 6 electrons therefore with the alpha, 3 with the alpha spin, 3 with the beta spin are going to take place in 10 dq. Now thereafter you can see from here that if it is a weak case, weak field case, then this is not going to happen, and this is what we have understand. This diagram, particular diagram is also very important. When the field is increasing from left to the right, we are going to get the CFSE from minus 4 dq to be more stable than minus 24 dq. But when at a particular level, when 10 dq becomes equal to that of a P, thereafter with the increase in the field strength, what do we get is the low spin complexes. The same kind of calculations one can do for CFSE using a formula now minus 6y plus 0.4x del t. The same kind of calculations as we did for octahedral can also be achieved for tetrahedral complexes. Just look at this. If there is a 1 electron here, now it's E and T2 energy states. So electron starts filling into E1, in the D2, E2, in the D3, E3, and you can just keep on calculating. E3 means 1, 2, third electron. Remember, in tetrahedral complexes, it is the high spin complexes which are always formed. So third electron do not get paired up in the E state, rather third electron goes into the E state, the T2 state, and therefore all the 5 electrons once got filled into 2 of the E and 3 of the T2. Ultimately, then the pairing starts from the D6 state. When the pairing takes place, one can easily calculate the CFSE based upon the number of electrons. You can also see the S values that will help us to understand the magnetic moment. And the calculated CFSE value for all these tetrahedral complexes keeps increasing, but as third electron enters into destabilization state, it decreases, then it further decreases, up to D5 it reaches 0. Once again with the pairing, it starts increasing and then decreasing, and D10 configuration is achieved. And ultimately, based upon the number of unpaired electron, for all these complexes, tetrahedral complexes, we have high spin state, and CFSE can be calculated as we did in the octahedral complex. The formula I have already shown to you. Using that formula, one can get the CFSE for octahedral and tetrahedral. It doesn't mean that for other geometries like square planar or for TBP, etc., we cannot calculate. But for the sake of simplicity, we have restricted our discussion to these 2 geometries which are more encountered. One can use the CAF crystal field splitting diagram for those particular geometries also, so as to calculate the CFSE. Thank you very much.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Bhagi for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.